Hello everyone, welcome to Microsoft Research Summit 2021. My name is Yu Cheng. I'm a principal researcher in Microsoft Research. Today I'm going to talk transformer efficiency from model compression to training distillations. We know transformer models have been dominant in AI area in recent years. Models like BERT, GPT, and the recent vision transformers have been achieved a lot of success in several domains, including computer vision, natural language processing, and speech recognition. One of the challenges of transmodels is the computation efficiency. Usually, it requires a lot of large model and a lot of training sets. However, how to make the transformer models more efficient is one of the biggest challenge to make it into real applications. My team have been working on the transformer efficiency from 2019. We have working on several kinds of topics like model compressions to make the model smaller, and also we do something called efficiency training, like BERT efficiency training and GPT-3 efficiency fine-tuning. Today, my talk will cover most of those topics. The first technique we use for model compression is the knowledge distillations. It's just naturally reduce the number of layers in transformer models. For example, we have BERT large models and BERT base models with 25 transformer layers and 12 transformer layers. You can reduce them to smaller layers transformers like 6-layer BERTs and 3-layer BERTs. Another technique we use called pruning. For transformers, we have two types of pruning. The first one is just you did for CNN or STM called unstructured pruning. Naturally prunes the neurons in transformers. Another pruning called structural pruning. This is special for transformers. We will reduce the number of attention heads and the dimension of the MMP layers, also some like KN layers in transformers, which reduce the transformer structurally. I'm starting to recording the first work we did for knowledge distillations called PKD, patient knowledge distillations. For PKD, we follow the traditional knowledge distillation framework, which have two laws, like the task-specific laws, to make a prediction accurate on the training examples. And also, we have this called student-teacher laws, which just mimic the student behavior with the teacher models. Specifically for models like transformers, which have deep transform layers, we have another loss called the intermediate measure loss to measure intermediate behavior between the teacher model and the student models. These two type of intermediate layers calculations, which we have called skip. Just you do student and teacher model skip layer to match them together, and also we have the last type called PKD to match the last layer of the teacher and student model. Empirically, you find they work better than last. In the result, you can say that on different training sets, we find the patient distillations actually works better than knowledge distillations. Also, in the glue benchmark, we saw you have a 6-layer PKD and a 3-layer PKD, which are very close to the baseline of the BERT's 12-layer models. After PKD, we are going to transfer to another topic, which is following up work for PKD called Accordia, Contractual distillations and intermediate representations. The difference between PKD and Accordia is just how you measure the intermediate loss. We know that in the PKD we use L2 norm to measure the intermediate representation between teacher model and student models. But actually, L2 is the good measure for the hidden states. Instead, in Accordia, we use something called the contractual loss to match the intermediate layers, which are just you have the intermediate layer of teacher and student models, and to match them use the officially like info NCE loss. So you can do this for fine-tuning, and also do this for pre-training, and just pre-training take more time. And in the result, you can say on the glue, cordial fine-tuning and cordial pre-training actually better than the PKD. And once you have like a combined fine-tuning and pre-training cordial, you can even achieve a better performance than any other base size. After we do compression and pruning, I also think about the efficient fine-tuning or efficient training. The work called early birds actually we will have done for the bird models. The idea comes from the local TK hypothesis, which assumes that you can get a sparse network at the beginning of the trainings. And also we follow another work called early bird tickets, which we can do this in structural ways. We use network slimming to reduce the number of attention head on the MLP layers to structure prune the bot models. After that, we have sparse models, but the same number of training data, so can reduce the number of training epoch and the number of training iterations to further reduce the fine-tuning or training time. In the result, you can say in the fine-tuning stage, we can reduce 40 to 45 time saving and achieve a very similar performance than baseline models. Also, this observation is held for the pruning pre-training stage. After we do several things for NLP, we also do one thing for vision transformers, which is very hot recently. For vision transformers, first we did this dynamic efficient training to pruning to further reduce the pruning time, and also we do something called model plus data co-explorations to reduce both model and the data parameters. This is the framework for SVIT, and you can see we do structural pruning and unstructured pruning, also the data pruning. In the results, we can say different pruning will give very similar performance than baseline while saving 30 to 40 training time or inference time. Finally, you can see some we show for we do the data co-explorations. The feature work into several parts. First, we are very interested in GPT-3, which we think is the major pain to do for apply it to real work. We need to compress, and also we do some neural actor search and jointly work to combine pruning and quantization for different data, not just the NLP vision, but something like multimodals. That's also my work. Thank you, and if you have any question, you can ask.